So hi, my name is Vivekanand, and I'm a part of the Ashton Gradial Spatial Orientation Lab. One of the co-directors, Paul Dizio, is here as well. And today I'll be talking about vibrotactile feedback as a countermeasure for spatial disorientation. But first, to set the mood for Valentine's Day, I've got a few romantic words here. Back in the infancy of humanity, when we would lay gently cradled in the arms of Mother Earth, gently gazing into the vastness of the twinkling nighttime sky, we would deeply question and wonder and genuinely dream, what is out there? And yet, space exploration was beyond the grasp of our biology, and so it became the unreachable domain of our mythology. And then came a time when humanity, we became pregnant and gave birth to our child, technology. And together with our child, we were finally able to reach into space and take our miraculous first steps upon the moon. And then technology turned into a teenager. And now my greatest Valentine's Day hope is that technology and artificial intelligence do not replace humans in space exploration, but rather enhance and augment the human. Because I believe that space exploration is part of the human journey and the human destiny. So there are two questions I'm going to try to explore in this presentation. The first is, can technology actually augment human performance in a spaceflight-like condition? And secondly, what kind of training can bind together human and technology so that when humans cannot rely on their own sensory system, they can rely on these devices? And the way I'm going to try to answer these questions is focused on the problem of spatial disorientation, which is something that astronauts will face. And spatial disorientation is when you lose sense of which way you're oriented. For example, where up might be. And you can imagine that that could be a problem when you're trying to land a spacecraft upon the surface of the moon. And just to highlight what a big problem this is, forget space exploration. Here on Earth, one of the leading causes of fatal aircraft accidents is spatial disorientation. This is where pilots and passengers are dying. So it's a pretty big deal. And the first part of this talk, what I'm going to try to talk about, is how I create many different disorienting spaceflight analog conditions where people cannot rely on gravitational cues. And in the past, in the lab, we've characterized performance and learning in this spaceflight condition. We've looked at individual differences. We've developed a variety of different countermeasures, including those with artificial intelligence. And the second part of the talk will be on, does vibrotactile feedback help? And vibrotactile feedback is putting little vibrators on your skin that vibrate information to you while doing the task. And this is based on a lot of great work that people in the community have already done. So how do I create these different spaceflight analog conditions? What I do is I strap living human beings into this machine that's programmed to behave like an inverted pendulum. So if you do nothing, it just falls over to one side or the other. And then participants are told to grasp that joystick and to the best of their ability balance right at that center balance point at the gravitational vertical. Now, if you notice here, I'm blindfolded, and so in terms of sensory information, what they're receiving is information through their vestibular system, and to a secondary extent, the touch receptors on their skin as they push against that machine. As a quick review, the vestibular system is located inside your inner ear. It's composed of your semicircular canals and your otolith organs. Your otolith organs are these fine little hairs that tilt, or they deflect as you tilt from gravitational vertical. They detect other things too. The further you tilt from gravitational vertical, the more they're going to deflect. So in this condition here, which I call my Earth analog condition, even though people are blindfolded, they have a pretty good sense of where they are, because the more they deflect away from gravitational vertical, the more those hairs are going to deflect as well, telling them where they are in space. And in this way, they're able to use gravitational cues to get a good sense of where they are in space. But in my second condition, which I call the 0G microgravity analog, I take these people, I put them on the back, all the dynamics are exactly the same. So why is this different? Well, if you remember the Earth analog condition, the more you tilt it, the more those hairs deflected, so you always knew where you are. But in this condition, those little otolith hairs are pointing down, saying you're at the back. And you can be at the balance point or really far away, it doesn't matter. Those hairs are just saying you're on your back. And as a result, you can no longer use gravitational cues to get a sense of how far away you are from the balance point, and so you become very disoriented. And this is why we call it a 0G or microgravity analog. So these are the two extremes. We have an Earth analog condition where you have full gravitational cues, and then we've got this 0G condition where you have none. But what I can also do is tilt a person back pitch them back by 68 degrees, and then they're in that roll plane, and now they've got diminished gravitational cues as if you were on the surface of Mars. And then what I can do is pitch them back even more by 80 degrees, and now it's as if you're on the surface of the moon, at least in terms of gravitational cues that you're getting. So my first experiment, what I wanted to know is how is performance in spatial disorientation affected by different G levels? And the way or the experimental design I had is for the first 8 trials, where each of the trials were just about 100 seconds long, people are in the Earth condition, just so that they could learn how to use this machine and they could learn how these vibrotactors are working. And after that, they got 3 blocks of 4 trials where in randomized order, they got Earth, Martian, Lunar, and 0G analog conditions. Now there were 2 different groups. I had the control group that had no vibrotactile feedback, and then I had the vibrotactile group. And the vibrotactile group had 4 vibrotactors on each of their arms. So if they tilted, for example, 1 degree to the right, the first one near their shoulder would go off. By 7 degrees, the second one would go off. By 15 degrees, the third one. And by 31 degrees, the fourth one near their wrists. So this is a summary metric, the standard deviation of angular position. I have many metrics, but what this means is the larger it is, the greater your oscillations and the poorer your performance. And this is the control group who has no vibrotactile feedback. The way I like to read this graph over here is from right to left. So on the right there at 1G is the Earth analog. Small oscillations, great performance. But you can see by the time they get to Martian G, they're already performing pretty poorly and they're oscillating quite a bit. And then Lunar, it's even worse. And by the time they're at 0G, their performance is really bad and they're losing control. Now the question is, does vibrotactile feedback help or not? And that's the title of my presentation. And what we find is, yes, in fact, quite astonishingly and remarkably, this vibrotactile feedback works, and there's statistical significance even at Martian G. So my first conclusion is that vibrotactile feedback is an effective countermeasure for spatial disorientation in partial G conditions, and even at this minimal level of exposure and training, these people only got 8 100-second long trials to get used to the vibrotactors, and still they're performing better. Now, in my prior work, what I've shown is that there's a characteristic pattern of spatial disorientation in my task. And what happens is, in the Earth condition, when they're balancing, they're very centered around the balance point. In the spaceflight conditions, they start to do this positional drifting, where they get further and further away, they have no idea that they're getting further and further away, and then they'll hit the crash boundary. And so I can quantify that as a signature of spatial disorientation, and we see the same results here, that vibrotactile feedback is able to reduce this signature of spatial disorientation in performance. Now, some really cool things can happen when I start asking them about their perception. And one of the questions I ask them is, rate your level of positional confusion, where 10 is I have absolutely no idea where I am in space. And again, this is the control group, reading it from right to left. At 1G, they're low numbers, they're not confused at all. By Mars G, they're already starting to get pretty confused, and by 0G, they're wicked confused. And many of them start to get all sorts of weird perceptual illusions where they feel like they're completely upside down or doing 360s. It's very unusual. Now let's see what happens with the vibrotactile group. And it's surprising, because the vibrotactile group is just as confused as the control group. Vibrotactile feedback at this level of exposure and training is not improving or changing perception. And in fact, by 0G, more than 90% of the vibrotactile group is reporting conflict, where they feel like they're in one location, but the vibrotactors are telling them they're in another location. So my second conclusion here is that vibrotactile feedback will introduce a feeling of conflict. This may not be bad, but it's important to know that this will exist, and likely this will increase as G level decreases. The other interesting thing is that I get the exact same thing when I ask them to report velocity, which is unusual if you know how the canals work at different pitch angles. And this may be an interesting collaboration with any sort of modelers who may be interested in trying to see if their models predict this. Now, the main thing I want you to kind of take away from this is that even with positional and velocity confusion, the vibrotactile group is still able to use vibrotactile feedback to enhance performance. And some of the future experiments that we're exploring in the lab is that how important is this conflict? Can you coexist with the conflict? Or do you really need a change in perception? And if we need a change in perception, what do we need to be able to do? More training or different sensory information? What is required? The next set of questions I was interested in is, what if we gave the participants tons of exposure and practice with the vibrotactors and the Earth analog, and then we throw them into the spaceflight condition? What happens then? Or what happens if you give them extended exposure in the spaceflight condition with the Vibrotactors? Do they show continued learning? Now, some of this stuff I've already presented last year, but it creates a nice storyline. And we've published this already, so I'll go through this quickly. But I had 3 groups in this experiment: the control group, who did not have any vibrotactile feedback, and then the vibrotactile and training groups who did have that. And everyone went through the same paradigm. On day 1, they were in the Earth analog condition. Now, instead of being in there for only 8 trials, they're in there for 20 trials. They're in there for 40 to 50 minutes, trying to balance themselves, learning how these vibrotactors work. And then on day 2, I plunged them into the 0G condition. And again, they're in there for about 40 to 50 minutes. So very quickly, the vibrotactile group performs much better than the control group, reconfirming that vibrotactiles are a good countermeasure. However, even with this extended exposure, what we're finding is that initially when they're put into that spaceflight condition on day 2, they're losing control, and still their performance is much worse when compared to the Earth condition. And 90% of participants are still reporting conflict on day 2. The most surprising and baffling thing for me was on day 2, the vibrotactile group had 40 minutes to learn and improve, and yet they showed almost no or very minimal learning and improvement. And I asked them, like, do you know you're disoriented? And they're like, yes, we know that. And then I would ask them, well, rate your level of trust in the vibrotactors, and they would all rate like 84% or higher. And I was astonished. I'm like, if you know that these vibrotactors, or you trust them, why are you not able to use it? And what the conclusion that this brought about is that for sensory augmentation devices, cognitive trust likely gained through training on Earth may not equate to reliance in a spaceflight analog condition. And so now the question was, well, how do you build this bond between human and device? How do you bridge this gap between cognitive trust and fast-paced, gut-level decision-making in a stressful, disorienting task? And so I looked at the sensory substitution literature for insight, and what they say is do active sensing, more exposure, but we did that. And part of the reason why the sensory substitution literature may not have answers is because majority of that literature tests and train in the same environment. But space exploration will demand us to train in one environment and test in a novel one. So then what kind of training should I do? I looked at our own work. Part of it was that you have to teach people how to disengage from their vestibular sense, which is giving them erroneous information. And the way that we teach people to disengage from it is we put like a new group, a training group, into the machine, and then what happens is we randomize the balance point, so they don't know where it is. And what this demands of them is to almost disengage from their instinctual desire to be at gravitational vertical, and instead focus on those vibrotactors to find where that balance point is. And once they do this, the training group performs way better, statistically better, than both the vibrotactile and the control groups. More importantly, they show very significant learning on day 2, which the vibrotactile group wasn't able to do. So my fourth conclusion is that exposure training will not be sufficient to bridge the gap between trust and reliance in sensory augmentation devices. Instead, we need more research, and we really need to think about specialized training when we think about sensory augmentation devices. Even with all of this benefits of the training program, 90% of them still reported conflict. And the training helped them overcome this at a deep level, but it did not change their perception. And a lot of what we're looking at the lab is figuring out how do we quantify this spectrum between sensory aid that requires a lot of cognitive effort to sensory augmentation, where it's kind of natural and you feel like you're immersed and one with it. And one of the future experiments we're doing is repeating this experiment with extended exposure, but in Martian G, where you have a little bit of truth, you have that diminished Q, does that vibrotactile information sharpen your senses? I've also really believe in community, engagement, and so I have a whole poster on that, a little bit of fashion, dance, science, all of that stuff together in sensory augmentation devices. So you can check out that poster or come talk to me. These are the conclusions I've already talked about. A great thanks to NASA HRP for the funding. Thanks to Trish for believing in me and giving me the postdoc many years ago. That's allowed me to be here. I love collaborating. I love talking to people, so don't hesitate to reach out. Thank you.